Hi everyone, let's do section 9.5 on the binomial theorem, which can itself be proven by induction, 9.4. And actually, you're going to do this in calculus as well, as we'll see. But this is in and of itself an interesting algebra problem. So how do we expand a plus b all to the n, where n is a non-negative integer? And in fact, I claim that by the end of this section, you're going to be able to work out a plus b all to the 10th with the help of a scientific calculator maybe, and you can do it within a couple minutes, accurately. All right, in the beginning, a plus b all to the 0, assuming that a plus b is not 0 itself. A plus b all to the 0 is 1. Remember, 2 to the 0 is 1, 3 to the 0 is 1. Likewise, this thing to the 0 is 1. A plus b all to the first is just a plus b. A horse is a horse. The square of a plus b, folks, it's not just a squared plus b squared. Please remember this middle term here. Don't be like these bad kids. Remember, don't be like these bad kids here in the lower left panel. All right. The square of a plus b is a squared plus what? Plus 2ab, plus twice the product of the two terms, plus the b squared. Now back in your Algebra 1 class, to find the cube of a plus b, you could take basically the square of a plus b, which was this thing over here, and multiply by a plus b, and distribute like crazy. So what you might do is take the square of a plus b, substitute in, well, take the square of a plus b, substitute it by this over here, all right? And then multiply by a plus b, distribute, combine like terms, and you get this. And by the way, see if you can figure out a pattern here. We're going to talk about this. A cubed plus 3a squared b plus 3ab squared plus b cubed. Now, of course, an Algebra 1 student would take some time to get to there, right? And at this time, you might need some time to get to here, but try to see a pattern, especially with the variable parts. Try to see a pattern. We'll talk about this. Now, in an Algebra 1 class, if you're asked to expand out the 10th power of a plus b, oh yuck, that would take you quite a long time. But again, I claim to you that maybe with the help of a scientific calculator, you'll be able to do this within maybe a couple minutes accurately by the time we're done with this section. Oh, now by the way, there are some geometric representations for these. I believe this came from the art of mathematics. So we can imagine the first power, the second power, the third power, even the fourth power as representing a combination of pieces here. So the square, a plus b all to the first, you're just adding lengths of line segments. The square of a plus b is like you're adding areas, right? The square of a plus b is not just a squared plus b squared. You also need these purple pieces over here, right? The 2ab pieces here. The cube of a plus b you can interpret in terms of volumes of these pieces here. The volume of the cube equals the sum of the volumes of these various pieces here. This is called a tesseract. If you've ever read A Wrinkle in Time, it's like moving a cube through time, maybe. maybe moving a cube through time, or just physically moving a cube, kind of thinking of it that way. All right. 4 dimensions. All right. Anyway, look for the patterns. Let's go back to the cube of a plus b. Look at the variable parts of the terms. You can ignore the 3's for now. Although it's no coincidence that 3 is the exponent over here and here. Now, if we expand out the cube of a plus b, it's not surprising that we start with a cubed, usually, and we end with b cubed. Bearing in mind that you have the right to reverse the order, right? We have commutativity here. You can switch a and b, and there's a symmetry that works here between a and b. But in any case, we normally start with a cubed, the cube of the first term, and we end with b cubed, the cube of the second term here. But as we move from term to term, look at the variable parts. what happens to the exponents on A? What happens to the exponents on B? Well, over here, it's like we have an invisible b to the 0, which is 1, right? We have an invisible 1 here for b to the first. Over here, we have an invisible a to the 0. I guess I should put that here. We have an invisible a to the 0 and an invisible 1 over here, right? So what's happening to the exponents on a? Well, we're going from a to the third to a to the second to a to the first to a to the 0. Maybe I should put these pieces in blue. A to the first here, a to the 0 over here. A to the 0 is 1. And let's assume for now a and b are not 0. Remember, 0 to the 0 is weird. So the exponent on a is going down 1 by 1 as we go from term to term, the way we normally write this. What about the exponent on b? Well, we start with b to the 0. We then go to b to the first, then b to the second, then b to the third. So basically, at each step, as we move from term to term, the exponent on a goes down by 1 with each new term, and the exponent on b goes up 1 with each new term. And notice also that the degree of each term is 3. Okay, because remember, to get the degree of a term such as these, you add the exponents on a and b. So here, of course, a cubed has degree 3. That's no problem. But the a squared b term here, this also has degree 3 because the degree on a, the exponent on a is 2. The exponent on b is 1. The degree here is 3. 1 plus 2 is 3. Over here, b cubed has degree 3. So each of these terms has degree equal to the exponent over here. All right. Each term has degree 3. So in general, when we consider a plus b all to the n, where n is a whole number, a non-negative integer, we start with a to the n, we end with b to the n, and we end up with n plus 1 terms after we combine all like terms. Notice here that when we had the cube of a plus b, we had 4 terms, right? But for example, the exponent on b goes from 0 up to 3. For emphasis, I'll emphasize the exponents on b. B to the 0, b to the first, b to the second, and b to the third. All right, we have 4 terms here, not 3. So we have n plus 1 terms. All right, the number of terms is the exponent here, plus 1. Now, what about the coefficients? All right, so we've talked about how to get these variable parts here. And by the way, I'll give you a moment to write down the variable parts for a plus b all to the 4th. So if you were to do a plus b all to the 4th, what would be the variable parts, ignoring the coefficients for now? I'll give you 15 seconds. Okay, so we'll check on that in just a moment. What about the coefficients? Like, how do we know the coefficients are 1, 3, 3, 1 here? I'm going to erase all this for now. How do we know the coefficients are going to be 1, 3, 3, 1? How do we know these are going to be the coefficients? It's from something magical, something really amazing in math. They're given by Pascal's triangle, named after Blaise Pascal. Here are the ingredients. Now, you might remember Pascal's triangle from your old algebra days. How do you construct Pascal's triangle? You start with a tent of 1s, and you start with row 0 on top, by the way. And for every other entry in Pascal's triangle, all right, basically the way to look at it is that every time you have 2 consecutive entries, the sum of the 2 entries will be the entry right below. Every other entry is like the child. It's the sum of the two entries immediately above. So for example, well, this is Pascal's triangle, in fact. At the top, you start with row number 0. Here, n equals 0, right? The row number is n. We start with n equals 0 on top. There's just a 1 there. For n equals 1, we have a pair of 1s. For n equals 2, we keep building this tent of 1s, but there's an entry in here. Now, how do we get the 2 here? We get the 2 by taking the sum of the two parents. Every time you have two consecutive numbers in Pascal's triangle, they give birth to their sum. 1 plus 1 is 2. Try to figure out row number 3. It will ring a bell. For row number 3, again, we have a tent of 1s. We have a 1 on the left edge, a 1 on the right edge. All right. 1 plus 2 is 3. And also, 2 plus 1 is 3 over here. Every time we have a pair of consecutive numbers in Pascal's triangle, they give birth to their sum. And we place that number below and in the middle, horizontally. Now notice here, for row number 3, we have 4 terms. For row number 2, we had 3 terms, okay, or numbers. So notice that for row number n, we have n plus 1 numbers in Pascal's triangle in that row. That corresponds to the fact that, remember in the expansion, if you're expanding a plus b all to the n, you have n plus 1 terms over here. For example, for a plus b all to the third, we have 4 terms over here. All right. For row number 4, we go 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then the 1 over here. And we could go on and on and on. For a plus b all to the 10th, you would go to row number 10, which is the 11th row in the triangle. Notice we have symmetry. We have symmetry about this central axis. That explains why. Over here, for example, see, it's okay if you switch A and B. There's a symmetry. You can go either this way or this way. All right, 1, 3, 3, 1, you have symmetry among the coefficients. All right, so row n gives the coefficients for a plus b all to the n. The square of a plus b, the coefficients are 1, 2, 1. Look over here, 1, 2, 1. Okay, these bad kids should have known that. It's not 1, 0, 1, it's 1, 2, 1. All right, now the cube of a plus b, all right, we had the variable parts. Now we know the coefficients are 1, then 3, then 3, then 1. Now, when I asked you about a plus b all to the 4th, you should have gotten the variable parts, okay? Now attach the coefficients. I'll give you a moment to do that. Give you 10 seconds to attach the coefficients. All right. Here is a plus b all to the 4th. We typically start with a to the 4th and we end with b to the 4th. The variable parts. Okay. As we go from term to term, the exponent on a drops by 1 each time. A to the 4th, then a to the 3rd, then a to the 2nd, then a to the 1st, then a to the 0, right? The exponent on b increases by 1. So we go from b to the 0 to b to the 1st, to b to the 2nd, to b to the 3rd, to b to the 4th. By the way, it's very easy to make a mistake. For example, you might get confused and you might end up increasing both exponents or decreasing both exponents. One way to do a quick check, make sure that the degree of each term is n, the exponent over on the left. In this case, the degree would be 4, right? Degree is 4 here. Here, 3 plus 1 is 4. 2 plus 2 is 4. 1 plus 3 is 4. And the 4 over here. Each term here has degree 4 if the 4 is over here. That's a good check because a lot of people make a mistake. For example, they might go from 3 and 1 to 4 and 2, for example, and that would be a mistake. You can check the degree of each term to help make sure you don't make those kinds of mistakes. Because you're going down for one variable and up for the other variable, it gets confusing. And so on and so forth. All right. Now, at this point, you should believe me that you should be able to do a plus b all to the 10th with the help of a scientific calculator within a couple minutes. The variable parts, it follows a similar pattern. You're going to have 11 terms. Now, Pascal's triangle, that might take some time to write out. All right. Bear in mind, though, you don't have to go through the whole triangle, because it does turn out that for row n and entry r, where you start with r equals 0 over here, and you end with r equals n, or r equals 4 in this case, over here, the entries here correspond to binomial coefficients, NCR, these combination numbers. So 52C5 is going to be way down there, the 2.6 million or so. That's going to be way down there in row number 52, the 53rd row in the triangle. And in r equals 5, that's in the 6th position, because you start with r equals 0. R equals 5, that's going to be in the 6th position from the left. And that's going to be the 2.6 million or so, the number of ways to get 5 cards out of 52. This here, Pascal's triangle, is a triangle of binomial coefficients, these NCR values that we mentioned before in section 9.6. All right. And it explains the symmetry also. Okay, now you can expand general powers. So for example, if you have the cube of 3x minus y, you might want to do a substitution and then use the binomial theorem. All right. So we have the cube of 3x minus y. You could let a be 3x. Let b be the opposite of y, because we like to have the sum in there, right? So 3x minus y is 3x plus the opposite of y. All right. You cube all this. Okay, do the substitution. The cube of a plus b. They should look familiar from before. Then sub back using parentheses. I'll put this in red. A lot of people forget the parentheses. Replace a with 3x. Replace b with the opposite of y in parentheses. Right. Simplify. All right. And we end up with this over here. Again, put grouping symbols where necessary. Remember, if you have a cube deal here, in a typical situation, you end up with 4 terms over here. So you can use the binomial theorem to work out these kinds of general powers, if you wish. Finally, where do we see these things in calculus? Let's say, for example, f of x equals x cubed. You might want to find the difference quotient, and in calculus, you may have to, right? Rise over run, f of x plus h minus f of x all over h. Remember? Okay. You have 2 points on the graph of f. You want to know the slope of the secant line. All right, here's x plus h. Here are the corresponding function values, the y coordinates. So here's f of x, which is the y coordinate over here, and f of x plus h, which is the y coordinate over here. All right, the slope of the secant line. And what is f of x plus h? Be careful. It's not, don't engage in wishful thinking. It's not x cubed plus h. Trust me. What is f of x plus h? When you see this, think what S word? Think substitution. You're going to substitute x with x plus h. Substitute x with x plus h. So you get here not x cubed plus h, but the cube of x plus h. You replace the x, it's like a kernel of popcorn, it explodes, and you get x plus h as the base. You're cubing x plus h now. Hey, how do you cube x plus h? The good old binomial theorem. Okay, it looks very similar to what we saw before, except you have an x and an h instead of an a and a b. Proceed. If you take the limit as h, the bottom approaches 0, as the run approaches 0, you're going to get the slope of the tangent line. The slope of the tangent line, and that's given by the derivative, which is 3x squared. That's the slope formula. For various values of x, well, Remember, the graph of y equals x cubed looks like a snake, like so, right? This is the slope formula. The slope at x equals 0 is, plug in 0, you get 0. The slope at the point where x equals 1, the slope of the tangent line, is going to be 3. That's the slope of the tangent line at the point where x equals 1. All right, you're going to see this stuff, the binomial theorem, when you're working out the derivatives of polynomial functions using the limit definition of derivatives, which employs difference quotients. Now, bear in mind, you might be going, wait a minute. It's like man overboard. 3 men over here. Okay, man number 3 drops down. 2 men left on board. Does that extend? Yes, it does. It's a shortcut. What's the derivative of x to the 4th? Take a wild guess. What's the derivative of x to the 4th? It's going to be 4x cubed. That's a shortcut, but you should be able to prove it. Now I'm going to show you some really beautiful and brilliant properties of Pascal's triangle, which is really one of the most remarkable things in math.